Oh, we're going.
We're going.
Is it going?
Yeah.
Okay. Okay, guys. So, I'm just gonna kind of indicate how we're gonna proceed with this. So, we're gonna start off with a review. We're gonna go over wavelengths and frequencies, and then we're going to discuss how waves interfere with each other. And then we're going to talk about specific waves, so electromagnetic waves. And then we're going to talk about refraction after that. So to start off with, does anybody know what a wavelength is defined as? So if I draw this.
Well, a crest and a trough.
Right. So what's that?
Trough.
Yes. And that?
Crest.
Exactly. What's the wavelength defined as then?
The distance between the two?
Between two.
Beginning of the
Two
crest.
crests, where it repeats the period of the wave.
Yes, exactly. Where it repeats. So the distance, the delta D between two crests or two troughs, we define as the wavelength, and we use the symbol lambda typically for that. Okay? Now, the time it takes to do one full cycle, does anybody remember what that's called?
Frequency?
Period.
Yes, those are both very interrelated. So the time it takes is called the period. So the delta t, the time, between this point as it travels to that point is defined as the period. The frequency, as Blake pointed out, is related to how many of these waves go by in a certain amount of time. So consider ripples on a pond. Say a stone falls here, and we have the ripples travel outwards. If I'm sitting here with a recorder, and I let 10 seconds go by, and 5 wavefronts hit in that time, what is the frequency of that? How many wavefronts per second have happened?
You said 10 minutes, 5 waves.
10 seconds and 5 wavefronts. So how many wavefronts per second happen?
1.5.
Exactly, 1/2. So it takes 2 seconds for each wavefront to arrive. 1 divided by 2 is 1/2. Since the number of waves has no units, we just define it as number per second, but number has no dimensions, so no length, no time, so it's just 1/seconds for frequency. A much more convenient way to define frequency is to say, well, we know in one period, big T, 1 wavelength goes by. So that gives us or maybe more intuitively, so the number is 1, the number of waves, and the time is big T, the period. So we get the frequency is just 1 over the period. Okay? So I'm just going to erase, if anybody's taking notes. Okay, so next up, we want to define something called interference of waves. So let's say we have one wave traveling to the right, and one wave is traveling to the left, and they meet here. Does anybody know what happens? Yes, they'll build. So if this has an amplitude A, and so does this one, the resulting wave will be what? How tall will the resulting wave be?
2A?
2A, exactly. So you'll get twice the height. Okay? Another example. Okay? This time, one is traveling to the right, one is traveling to the left. But this time, this wave has a crest in the down, and this one has a crest at the top. So that a trough, essentially, is meeting a crest. What happens then?
Some cancellation.
Yeah, they cancel each other. So if they both have the same amplitude A again, A minus A is 0. So they'll cancel each other out. Okay? Now we have to talk about a specific type of wave now. It's an electromagnetic wave. I'm going to use two different colors to describe it. This is something we will have already gone over last week. So an electromagnetic wave is a wave that consists of oscillating electric and magnetic fields, which are perpendicular to each other. So here, if this is the electric field, use an E for that, and this is going up and down, then the magnetic field is doing the same, but out of the board and then into the board. This is an electromagnetic wave, and since we know that electromagnetic waves are also light, as well as X-rays, gamma rays, and so forth, we know that they all travel at the same speed, c. V for velocity, and we use the speed of light in a vacuum, and that'll be really important in a second. In vacuum, the speed of light is a constant 3 times 10 to the 8 meters per second. That number is not as important as to know that all waves travel at the same speed in vacuum. That's what I want you guys to take away. Okay, so we're going to talk about what happens to an electromagnetic wave as it goes from one medium into another medium. So the light ray enters. I'm going to have to erase this again. We have two different mediums. So the light is going to come in, say, from the vacuum, we'll use that, or from air, or what have you, and it's going to enter a different medium. So glass, water, anything like that. So the first thing we're going to do is draw a line perpendicular to the surface that it's entering, so 90 degrees. We use this line to measure the angles at which it enters and then the angle at which it travels relative to as it goes into the medium. And what we observe is something called refraction. So it goes into the medium, and what happens is it slows down, so the light will actually travel at a speed that is less than the speed in vacuum. And secondly, it'll bend. And we're going to discuss why that happens in a second, but first I want to set up what it'll actually look like. So first we say that the light enters at a relative angle to this line, this 90 degree, what we call the normal line, the perpendicular line. And we use this index I to indicate that the angle that it's coming in at is incident. If it enters a more dense medium, it's going to bend towards the line of the medium. Towards the normal line. So we can define a second line in the new medium relative to the normal, and we indicate that it's been refracted. So we use the subscript R on our theta to indicate refracted angle, just like we used I for incident angle. It changes as it goes through. The speed also changes. So in vacuum it has speed c, but in this one it'll have some speed less than c. Let's define something that allows us to understand how much slower it is. So we define n, which we call the index of refraction, to be how much it's slowed down. So the speed that it travels in the medium divided by its maximum speed, which is the speed in vacuum. So what is this number going to vary between? What's its lowest? Yeah, 0 and 1. Because in vacuum it's at its fastest, and that'll be c. So c over c is 1. And then at its lowest speed, if you stop the light, not going to happen physically speaking, but in this definition, then it will be 0. So now why does this happen? Why would light become refracted? Why would it slow down and change essentially its angle as it enters the medium? Does anybody have any ideas on that?
Something to do with the particles, I imagine.
Definitely.
Mix of the particles.
The structure of the medium?
Yep, that definitely plays a part.
The charge or the electric field on the atoms in the medium?
Absolutely. So let's try a simplified picture of the electron and going around the nucleus. Let's just say this is the electron, and it's attached to the nucleus by a spring. We'll go back to our pond example. As the electric field varies, it's going to excite this electron. That electron is going to vibrate back and forth as it gets hit, and it's going to produce ripples of its own in the pond. Because the electric field is so here's how the picture looks with the actual atom. The electric field goes over the atoms inside of the new substance, and as the electric field acts, it's going to pull it this way. When the wave is then pointing downwards as the wave goes by, because as we know, it's going to oscillate, it's going to be pulled the other way. And the result is that it's going to start going up and down. Now that is going to disturb the water, or in this case, the electromagnetic field, and that's going to create waves of its own. Those waves interfere with the original ray that came in such a way that the resulting wave becomes bent and slowed down. Is that okay with everybody? Yeah? Okay. Now let's come back to this equation. What's constant in this equation?
C.
Right. So if we call Ni and Vi the incident speed and the incident index of refraction, and Nr and Vr the refracted incident index and the refracted velocity, we can rearrange. Oh, yes.
Isn't it C over V? Because we do have an index of refraction higher than 1, which is why, so, like right now, if N is greater than 1, which we can get in materials denser than air, if it's greater than 1, and then that means that this speed going through, the speed of light through a medium will actually, according by that equation, will speed up that moment. Isn't it the other way around? Isn't it C over V?
Well, what is the maximum speed that this V could take?
Maximum speed is the speed of light, right?
Right, so that would be 1. Is it ever going to travel faster than the speed of light through air or through a medium?
No, but if V, the maximum speed of V is the speed of light, then the maximum N can be is 1. But N can be higher than 1. I think it's C over V. So as V slows down, N increases.
You could define it actually either way, because it's a definition.
Okay.
You're trying to discuss, so in this case, we're thinking about it as how fast relative to its maximal speed it's going. I could, if I wanted to, because this is just a definition we're using for our convenience, define it the other way around. The numbers would vary in a different way, but this is just a convention. Okay. So from this, by setting it equal to the speed, c, it's constant on both sides. So we can say c is equal to v over n. Setting that the same on both sides, we derive this relationship, i.e. Vi over Ni is equal to Vr over Nr. Does that make sense? We just set it both sides equal to a constant, and since the same constant, okay? Now one thing doesn't change as it enters the new medium, and that's the frequency. That is the time it takes for one wavefront to travel one wavelength. So again, employ the exact same strategy. Frequency does not change. So let's set F is equal to V over lambda. That's constant in the first medium and in the second medium.
that's just a found phenomena that like frequency doesn't change when it travels through these mediums, so like the color obviously is the same, that's why.
It's actually a property of light in general. Light always has to travel. This issue is a little more complicated, and I'd love to go into it with you after class.
Sure.
But for the sake of this, I will discuss the mechanism behind it
Okay.
with you later. Okay.
Sorry.
Yeah, it's all good. It's all good. So, there's one final relation that my friend Patrick is going to go through with you guys, and you're going to derive it for yourself with experiment. So I would like to show that to you, and I'm just going to write it down. I won't derive it, and then we're going to use that to look at something. Right. Okay, so the ratio of the angles. The ratio of the angles will be related to how much the wavelength gets changed as it goes into the new medium. So we're going to do a quick demonstration. Where's the source?
The top is the one.
Yeah. Where's the prisms?
Oh, I have it right here. There's not a prism in the box there.
Okay. So what do you think, based on, first of all, can I ask you guys, what do you think the relationship is between wavelength and the color of light that you see?
Well, each color has its own specific wavelength,
Okay.
right? So as that changes, the color will change.
So what does that tell you about the equation on the board? We have a ratio of incoming angles equal to a ratio of wavelengths. What do you think that tells you about what's going to happen to the colors as I pass it through into a new medium?
Color will change based on the angle,
E-
relative to the angle.
Can you explain that a little further?
The angle of refraction will change the wavelength in a related manner.
So, yeah, okay, yes. We're going to put what you said maybe in different words. We're going to see different angles depending on the wavelength.
Yeah, sure.
They're going to refract at different angles depending on the wavelength. So that means we're going to see the different colors refract at different angles. This is a little tricky with this source. So, might need a few magnifying glasses. Okay, so, oops. Okay. There we go. So if you guys want to come up and just look.
So pretty.
What you notice, can you see that? There's blue on one side,
Roy G. Booth.
above, and red on the other.
Nice. Oh, did you say what on the other?
And red on the other. That's it. Yeah. It's not really like you can't really see it very well in this, but that's mainly due to the source of light that we're using. If we were not stuck in this classroom, we could go outside.
What if you do this? They're just gonna mess it up.
Yeah.
A little bit.
But you can get a little bit here.
Cool.
Okay.
Thanks.
Just read it in.
I can hear color. Hear color. Sorry.
And that brings us to the end of the intro.
Should I start a new video or just keep this
You
one?
have to make some individual videos.
Yeah, so,
I can just,